It does contain some information. As a matter of fact, I'm going to depart a little from what's on there because I woke up in the middle of the night and decided the best way to describe 10 years of research in 10 minutes is to get to the point. So I was, just a little background, I was a nuclear physicist during the nuclear power days of the 50s and 60s. I worked at Harlow, and then I was tempted away by IBM to teach scientific computer programming because none of their staff knew Fortran or any other mathematical language. And that got me into the financial world, and I worked for banks for the rest of my life. But when I retired in 1999, I went back to my first love, which was physics, and decided that it was about time somebody had a real fresh look at gravity, especially after reading Professor Lisa Randall's book, Warped Passages, in which she said that there are those who still believe that the inverse square law is due to the fact that we have 3 dimensions of space. And I thought that doesn't really make sense, because when I was handling radioactive sources, I learned that it was the solid angle subtended by your body that determined how much radiation you got, and gravity does not care about the size or density or shape of the target body, it's its mass. And I couldn't see how gravitons would know exactly how to be able to have an effect that depended on the mass of the body. So I started to look for to see whether gravity was caused by the conservation of energy and momentum. These are such well-established laws. It soon became pretty clear that in the 4 dimensions mentioned by the previous speaker of space and time, that you just can't have conservation of momentum, although conservation of energy is pretty easy. If I throw this up, if I can catch it, you can see that from the time it leaves my hand, it can have the same energy all the time, converting kinetic energy into potential energy and then back again. There's no reason why that shouldn't be done with the conservation of total energy. Well, momentum is another matter because it clearly changed momentum, otherwise it would have kept going and hit the ceiling. So how do we conserve momentum? Well, as I say, in 10 years you go through a lot of things. So I'd like to get right into what I believe happens when you throw something up like that. If you take the, you will see this. If you take the, no, I've got to, all right, I'll if you take the Earth, which is approximately round, with a 4,000 mile radius, and you throw something up. Well, let's take, the moon will be over here somewhere, and I just cannot believe that the Earth can have any effect on the moon now, and hasn't had any effect on the moon since it was ejected from the Earth as a result of a collision of some asteroid. But it has the same energy now that it had, or approximately the same as it had 4 billion years ago. So how did it go from an almost vertical trajectory into a circular orbit? Well, let's see what happens when I throw this up. If I'm here, throwing up the, and let's say it went up 4,000 miles, so we get some scale in it, because you wouldn't see the distance I threw it there, would not be showing here. So let's suppose I could throw it up to here. It goes up to there. When it gets to the top, it has no kinetic energy. This is all, I think, axiomatic, as Dr. Sheldon Cooper would say, you know, from Big Bang Theory. So it there loses, the energy is entirely potential energy, and I'm going to call that distance R0. My right arm doesn't go up that high. We can say that R0, which would be about 8,000 miles from the center of the Earth, is the length that represents potential energy for these masses. Now, it has the same energy when I threw it up. And as soon as it left my hand, it had that same energy. But clearly, how is it going to represent it? In other words, in what form is that energy? We know it's moving, but I'd like to be able to represent that kinetic energy in the form of a distance, a separation, so that we can compare apples with apples, compare that energy with the kinetic energy. So right away we need another dimension which represents a separation between bodies when they have kinetic energy. So let's say that that other dimension is the x dimension. And it turns out that the value of the coordinate is equal to some constant time times the rate of change of distance in space, so that torr times the velocity is equivalent to that distance. Now, that would mean to say that when this left my hand, assuming it's going to go up that high, then it will be have the same extension in the x dimension that it has up here. So it would be somewhere along this line. And since it is on my hand still, then it must be at this point. So that when is that distance the same as that? I think it is roughly. So when I release it, it moves in what is really a virtual dimension. In other words, I'm not saying it physically exists. But as I accelerate it, it moves this way until it's here. It still appears to me, because this is the only space dimension here. Get it up there. This is the space dimension, and this is the virtual dimension x. So the bottle appears in my hand here, but as soon as it leaves my hand, it's moving upwards, which means that it's in terms of the, now we have 5 dimensions. In fact, I think there are 9, but you don't need them all. If you add to space-time this x dimension, then it's here. But it has upwards momentum. And so it's traveling upwards, because remember, space is in this direction. It's at this location moving upwards. So the situation now, I made a bit of a mistake here. This distance is actually here. That is equivalent to R0. It's not quite as far as I thought, almost as far. It's actually here. It had upwards momentum, and it's located here, and it's tethered. So think of gravity as a tether, if you tie a dog to a chain and tie the chain to a big boulder in your front yard, the dog can run in a circle. And the energy is the dog's kinetic energy. So here we have this bottle traveling upwards here at this location. But it's tethered by the fact that the total energy cannot change. And that means that it will stay this distance away from the center of the Earth. So it performs an arc like this. And visibly, it goes up. But and follows, in fact, a cosine. Well, if you take this as the origin, it will be a cosine. And of course, then it keeps going. When it gets to here, now, although it's free to move in the x dimension, it's not free to move any further in space, so it lands back in my hand. So that, I believe, is the action that takes place. Now, you'll notice that the total energy is conserved, and the momentum is conserved. And that, briefly, is how it works. Let me push it at that point. Okay. So when the moon left the Earth, then, if we can go over here and talk about it, when the moon left the Earth, it went. It would have been struck from here somewhere by some asteroid, which I personally think may have come from the sun. But it collected some matter from the Earth and left some of its own behind and went on up. And went up for a distance that would be the distance of R0, which actually is the square root of 2 times its present distance. And then it would have begun a highly eccentric orbit around the Earth. And for reasons I can't go into, although it's on my website, fatherphysics.com. No one had apparently taken that website, and I thought I'd have the audacity to take it.
What is it?
It's called fatherphysics.com, and I've got about 20 videos on that. So anyway, it's actually due to either precession or time dilation, I'm not sure which, or if it's both, but eventually it ended up in a circular orbit. But what I'd like to do is to talk about this circular circle around the Earth. Is it right to keep going?
You have until 8:30, so 2 more minutes.
Okay, all right. All right then. To kind of generalize this, surrounding every body there is an invisible energy shell, I call it. And any object that has a gravity relationship with that body, this could be the moon, this could be the Earth, this could be Saturn, that could be the Sun. It stays on the surface of that energy shell, which has actually as many as 9 dimensions, but certainly needs 3. And the point I want to just say is that the moon now, if I take 2 dimensions of space, take R1 and R2, and this is the Earth here. The moon is on the surface of this as it has been since it started. First of all, in the X dimension, which now is out this way. It started out here. It's now on here, but it's performing a circle in this 2 dimensions of space. Viewed from a kind of angle, it would be like this. And this now shows you 3 dimensions. There's the X dimension, and then this, and this are the R dimensions. It's on the surface of the energy shell, going around like this. And it's this far in the X dimension, that's the R0, and this is its distance in space, which is equal to this, because that's an equilibrium state where it has that it has gravitated to, so to speak, in the forbearance of a year that it's been in existence. I'm sorry that's such a rush through, but that is briefly the theory I've come up with. And it's, I should have said at the beginning, I thought there might have been some students, but I don't think there are. If there are, I would have said to them, don't do this at home, or don't put this at school, because this is all not gone through a peer review. This is the first I've given any kind of peer review to it. So it could have serious flaws that I just haven't seen. But if there are any questions, I'll be glad to try and answer.